Accounts of glowing orbs hovering over dark, snowy valleys are often dismissed as mere folklore or optical illusions. In central Norway, the Hessdalen Valley functions as a highly instrumented testing ground for extreme atmospheric physics. Automatic measurement stations here have recorded structured luminous phenomena reaching up to 30 meters in diameter. These objects emit up to 19 kilowatts of radiant power, with appearances correlating strictly to local magnetic disturbances and ELF radio spikes. This energy output indicates a highly energetic physical system that demands rigorous, data-driven observation to decode. Hessdalen serves as an active laboratory, exposing gaps in our current thermodynamic models of the lower atmosphere. Standard scientific models categorize glowing, floating atmospheric orbs as thermal plasmas, clouds of superheated ionized gas. As a gas, a classical plasma follows strict thermodynamic laws, inevitably expanding and cooling as it interacts with the surrounding environment. However, years of photometric and spectroscopic data captured by automated observatories prove mathematically that the lights in Hessdalen are not classical plasmas. The measurements describe a structured, thermally self-regulated system that actively resists normal atmospheric decay. Decoding exactly how these objects generate 19 kilowatts of continuous power requires abandoning traditional gas models to reconstruct their mechanics purely from the optical data. We begin with the shape of the light. This 3D graph shows a classical Gaussian curve, the visual footprint of a typical plasma gas cloud. By calculating this intensity distribution, researchers can map radiant heat across physical space. Contrast that theoretical curve with the actual intensity distribution of the Hessdalen lights. Focus on graph B. The sloping profile of graph A is absent. Instead, graph B reveals a structure that is flat on top with incredibly steep sides. This steep-sided profile is the mathematical signature of a uniformly illuminated solid object, or a plasma contained by a sharply defined boundary layer. The emission profile indicates that extreme heat is being tightly contained within a regulated border, a result that contradicts the simple free electron plasma model. Applying the Stefan-Boltzmann law to an expanding plasmasphere, if it undergoes adiabatic expansion, its temperature must drop as volume increases. This increase in size causes radiated power to drop exponentially, rapidly dimming the sphere. The actual photometric data from Hessdalen tells a different story. This lower scatter plot tracks the object's image size against its total luminous output. As the physical size of the phenomenon increases, its brightness scales linearly with its area. The object gets brighter as it gets larger, which directly violates the laws of adiabatic cooling. Spectroscopic data confirms this temperature stability. Panel B compares the spectral peaks at minimum and maximum luminosity. Despite massive volumetric fluctuations, the peaks show no shift in wavelength or amplitude, proving the core temperature remains constant. Because the phenomenon expands without cooling, it must possess an internal, self-regulating heat pump mechanism that defies classical thermal mechanics. This creates a central puzzle. What physical model sustains a sharp boundary and a constant temperature during expansion? One hypothesis, proposed by John Abramson, suggests these objects are spheroids constructed entirely of glowing silicon nanoparticles. This model requires massive electrical discharges, like lightning, to strike the ground and vaporize silica directly from the Earth. This model is unsupported by the evidence, as no lightning strikes have ever been detected in the valley during these anomalous events. David Turner's electrochemical model offers a viable framework. A hot plasma core draws in ambient aerosols, creating a chemical reaction boundary. Hydration processes at this edge act as a thermochemical heat pump and insulator, maintaining the sharp temperature gradient. Turner's model also explains the non-adiabatic scaling. Panels A and B show a central core surrounded by distinct satellite spheres of different colors. The expansion, seen from a distance, is actually the rapid formation of new condensation nuclei, a cluster of smaller, thermally regulated orbs gathering around a primary seed. This complex chemistry also explains the object's specific spectral peaks. The observed spectrum in graph A closely aligns with the simulated emission profile of artificial semiconductor LEDs in graph C. The leading hypothesis suggests the central plasma core acts as a high-heat catalyst, decomposing organic aerosols, like mold spores, into nanoscale structures. At this size, these particles act as quantum dots, emitters that use quantum confinement to produce the highly specific narrow-band wavelengths recorded in the valley. Turner's model aligns with the photometric scaling, the spectral peaks, and the sharp optical boundaries, identifying the anomaly as an active, self-regulating electrochemical reactor. The data reveals the true nature of the Hessdalen phenomenon, a highly dynamic cluster of thermochemically self-regulating plasma boundaries. Sustaining a 19-kilowatt structure in the open air requires continuous energy. In a valley dense with quartz, localized tectonic stress likely generates the piezoelectricity necessary to ignite and maintain the core. This counterintuitive survival against the environment is mirrored in other extreme terrestrial systems, like bloodfalls at the Taylor Glacier in Antarctica. At bloodfalls, extreme salinity and the latent heat of fusion allow an iron-rich brine to remain liquid and flow at -17 degrees Celsius, subverting the expected freezing point. Similarly, the specific geochemistry and atmospheric aerosols of the Hessdalen Valley create a chemical insulation mechanism, allowing a 19-kilowatt plasma cluster to sustain itself in the freezing sky without dissipating. The Hessdalen phenomenon functions as an extreme, isolated physical system awaiting proper mathematical characterization. When observed with the right instrumentation and modeled with accurate thermodynamics, the bounds of the impossible dissolve into rigorous structural physics.